Is fusing our bodies with computers and technology taking us closer to creating advanced forms of human life?
The cyborg is actually something that's part human, part machine, a cybernetic organism.
We're now looking at the compatibility between electronic systems and biology.
From the Terminator and Robocop to Star Trek's Borg, combining human biology with high-tech hardware seems pure science fiction. But are cyborgs becoming science fact?
The bionic man, for example, can now become a practical reality because the technology is there.
Darwinian evolution has got us the millions of years to where we are today, but with the new technologies we're going to have over the next decade or two, we'll be able to seize control from Darwin of our future evolution as a species and go the direction we want to go rather than just the survival of the fittest.
This is a major technological step that's allowing us to evolve to take ourselves forward.
The first steps forward in assisting our bodies with technology are not being taken by some huge science fiction character like Robocop, but by someone much braver. Born with a congenital defect of her left arm, Daisy Harriman found even the simplest tasks difficult, until now. Daisy was recently fitted with the world's first bionic hand designed for a child. Named ProDigits, the high-tech artificial hands took over 20 years to develop by British engineers and doctors.
There's nothing else in the world like the ProDigit hand that can fit patients with transcarpal hands. That's to say people who've got no fingers or no thumb or the distal section of their hand missing.
Too wide then?
Daisy's hand works by, she's got a little push button which is down at the distal end of her residual limb, and she pushes against it to make the hand open and close. One push makes it open and the next push makes the hand close. The motors and the gearbox are inside the fingers, and if you take the cover off, you can see inside there is the motor, and there is the gearbox, and the wires there that give it the signal to make it operate. When they come into the training school, they work with the occupational therapist, which is a very important part of the service. It's like me giving somebody a car and I'm not teaching them how to drive it.
Come in, here's the dolly. Good girl.
She likes to ride a bike. It gives her a bit more balance. Push a doll's pram, that's more balance. And she's just started trying to use the skipping rope. At school they do skipping, so we're trying with that.
Daisy's done very well because she was a little bit introvert in a way when she first came to us, and it's given her more confidence than she used to have when she first came here. After we'd fitted the children and we'd logged all the problems, we then thought it was a time to look at an adult.
I was climbing in Alaska. I was climbing Mount McKinley. It's the highest mountain in the USA, about 4 miles vertically. We were stranded just below the summit in a really bad storm, stuck in an ice hole overnight. I went off to organise a rescue the following morning. Huge chunk of ice broke away and took me down this ice chute. I fell for nearly half a mile vertically, and I broke both my legs on the way down. I was stranded out on the mountain for 2 days. Overnight, the temperatures went down to minus 50 degrees centigrade, and I was affected by frostbite. Frostbite took my left leg below the knee, half my right foot, and all my fingers and a section of the nose. Unfortunately, the only treatment for frostbite is amputations. How are you doing? All right, thank you.
And how's things going?
Oh, it's working well. Yes.
Stephen's hand is a more advanced hand to what we fitted to the children, because he's got 2 electrodes in the palm of his hand. That's you, that's fine. Okay. And there's the 2 electrodes that control it. Oh yes, you can see the marks where they're working on there quite nicely, aren't they? Yeah. One of them actually controls the opening and the other electrode controls the closing of the hand. And this is again operated by milliamps of electricity, which these little sensors sense when he actually operates the muscles in the palm of his hand. The motors are in here and the gearbox is in here, and there's a worm gear there that works on the toothed unit inside there. Now this is all mounted in silicon, and this is part of the unique part about it, is that it then gives you flexion to be able to flex your wrist, which is what you would normally do. You've got the 2 electrodes in the palm of the hand that control it, and of course to get in and out of it you've obviously got to have a zip to get in and out of it. You've got your battery in here, your lithium battery, and also you've got your electronics in this section here, and then all your cables are then built into the actual silicon to keep it all embedded in it. And of course over all of this goes the silicon, the cosmetic glove that gives it the realistic effect. It's more important to Stephen than it is for Daisy because he's got 2 limbs missing, so he does need something that he can grip and hold things with that he wouldn't normally be able to do.
I've come to think of ProDigits as a useful tool. People hear the whir of the motors, which are very gentle, but it does sound rather robotic. I don't think the ProDigits will ever replace a normal hand because it's a very, very intricate piece of equipment, but it's getting near to it.
Solving the problems of being disabled isn't easy. Evolution produces highly complex systems for basic human skills like walking or running. Can we even reproduce just one part of the leg?
An ordinary leg has up to 50 muscles in and around the knee to help a person walk. Our system, by combining hydraulics and pneumatics, emulates just a few of those muscles. It's called the adaptive knee because we feel it actually adapts to the way the amputee wants to walk. So rather than the limb controlling the amputee controls the limb. Ian Logue has been one of our trial amputees for at least 2 years now. He's been on both prototypes and pre-production and now production units and has seen the evolution of the product over that time.
The control is a big feature in this particular prosthetic limb. It provides assistance, it feels safe, it feels stable. You get the best of hydraulics, pneumatics and intelligence.
This is basically in essence the adaptive limb. This is the shin, and then within the shin you have the control cylinder, which is both hydraulic and pneumatic, and attached to the control cylinder and to the shin is the knee mechanism, which literally allows the amputee to bend the knee. This is basically the control cylinder which fits inside the shin. It comprises of a hydraulic chamber and a pneumatic chamber. The hydraulic chamber provides what we call the stance control, which for instance gives you an extra resistance when you're going down a slope or down the stairs. And then the pneumatic chamber basically acts like a spring almost, in that depending on the resistance that is set, it can actually have a very high resistance to swing, which limits how far the leg swings at fast walking speed.
Motion detectors and microcomputers control a combination of pistons, so they react like muscles and tendons to changes in speed and terrain. Each knee can also be tailored to individual needs.
You can program the functions individually, so for instance for coming downstairs, for walking down a ramp, for a stumble feature, or to give you an extra stance support and variable walking speed.
One of our latest products is the Mercury Foot, which basically comprises of 2 springs, a spring for the toe and a spring for the heel. An evolution of that foot is the Mercury Sports Foot, which not only has an extended heel spring and an extended toe spring, but also has an additional shock-absorbing spring.
I'm a former Army officer. I cleared mines for a charity in Asia and Africa. I was blown up 5 years ago, as a result losing my lower right arm and leg. For me, as an amputee user, what is different about this foot is the natural feeling I get when I run. And that's because they put a lot of work into making the carbon fibre spring transition very smooth. This is actually, it looks quite simple, but the design that goes into this is huge. They use a computer-aided design system, a CAD system, similar to the system they use for Formula One cars. The materials here are very high-tech. This is carbon fibres, airframe, aluminium, and a tungsten cylinder which contains a shock absorber. The design behind the spring technology has been very painstaking, and that is what gives me this natural feeling. It feels like a natural transition from heel to toe to leg lift. It feels like it used to feel when I had a foot. And the best feeling is a sort of feeling of freedom again.
ProDigits, the adaptive knee and Mercury foot, show massive improvements in restoring lost function to the disabled. But one London company is using air power to mirror our muscles. Their new robotic arm is truly a shadow of ourselves.
The important part is that because we've used the air muscles and bundled them up in the forearm, we can have all the movements, and we've in fact implemented all the movements that a human hand is capable of, even the raising of the little finger joint. I mean, the NASA hand can do 12, the human can do 22, and the shadow hand can do 22. So we've made a hand that, as it were, can be taken off and put somewhere else. So we call it a teleprosthesis, tele meaning far. So this hand can be doing something for you, or particularly for someone disabled, somewhere else, far away. The air muscle, which is something that we discovered back in the 80s and have developed ever since to do the sort of robotic tasks we need, is an extremely simple device. It is simply just a rubber tube, and round it is a piece of braiding that's woven crisscross braid. If we introduce some air under pressure, it contracts, and you will see it very easily bends a 6-inch nail. It does it very smoothly, and the movement is just like a human, and then we just let the air out, and it relaxes again. The nail is bent. We can make big ones for big tasks, like your legs or the legs of larger animals or devices, or we can make little ones just for little fingers and so on, just like nature, but we can't do it as well as nature. Nature is still ahead of us at every step.
Nature may still be in the lead, but cyborg science is catching up with evolution.
We've suddenly discovered that actually nature's invented a heck of a lot of really clever stuff out there in the 3 or 4 billion years of natural evolution. And some of the ideas in nature are so brilliant that we can't help but pinch these things in engineering terms and see if we can use those as a basis for new engineering developments.
Our senses are also crucial to survival. So how far can we now learn from nature to replace this sensory capability?
We've been working in this group in this so-called area of bio-inspired silicon. Now, effectively, what we've been trying to do is to model the physiology of things like the cochlea out of silicon. The cochlea is the heart of the ear, which when defective results in stone deafness. So it's not the hearing aid part of the ear, it's actually the brain of the ear.
1 child in every 1,000 is born deaf, and 17% of the adult population suffers hearing loss. Professor Tumazu's team thinks a single microchip can copy what a healthy ear does.
Sound waves enter the pinna or the earlobe, and these sound waves are then converted to pressure waves within the basilar membrane. Now, the basilar membrane is a very thin, fluid-filled tube, which effectively takes these sound waves and converts it into pressure waves along its length. Now, on the surface, we have 24,000 hair cells. And these hair cells are acting as mechanical to neural transducers, and they're the things that are sending the signals to the brain.
Instead of thousands of hair cells, the new computer chip will use just 8 low-powered filters to transmit sound signals to the brain.
This is the silicon chip. This is the bio-inspired silicon device that replaces the whole functionality of the cochlea. The chip uses something like 1/1000th of the power of a light bulb, and is only 2 by 3 millimeters in dimension. And so the whole of the processing of the cochlea, the physiology of the cochlea, is implemented out of low-power analog electronics. We're already looking at retinal implants, again applying some of the technology that we've been doing for the cochlea, but looking at things either subretinal or outer retinal prosthetics. And the technology is such that we can hopefully allow blind people to see, but with a technology that's cosmetically very, very friendly now. Unlike the experiments that were reported, say, I think a few years ago in the press with Stevie Wonder, for example. There we were looking at a retinal prosthetic device, but with a huge battery pack and a huge pair of glasses.
Whether we're disabled or not, Could inserting new technology into our flesh and blood have other benefits?
I think for years people have been looking at upgrading the human body in science fiction, yes, but way, way back in history, can we do something more with what we've got? Up till now it's been technology on the outside, for example a car to help us go faster. Now we're at the stage of actually taking it into the body.
Reading University looks like any college campus, but the head of its cybernetics department became the world's first cyborg professor.
In 1998, I had a silicon chip transponder surgically implanted in my left arm, and that was there for 9 days, which was what we wanted for the experiment. What that did was send out an identifying signal to the computer in my building at Reading, and we got the computer to open doors for me and say hello.
The implant triggered sensors in his university.
Hello, Professor Warwick.
Identifying him, opening doors, and constantly tracking his location.
Hello, Professor Warwick.
It's probably worse than punching the clock because you've got a choice with punching the clock. Here with an implant, you're tracked all of the time. You go to the toilet, you leave the toilet, the computer knows exactly when. Physically, I hardly felt anything after a day or two. It felt uncomfortable, but then it was okay. Mentally, it was a big surprise because I actually felt it was part of me. And because I had a computer sending signals to and receiving signals from the implant, somehow I felt a sort of affinity with the computer.
Having proved that implanted chips can transmit from inside the body, the Reading research is getting more ambitious.
The new experiment, we've been working on another implant. Again, this is going into my left arm. This time we'll have direct connections onto the nervous fibres in my arm, sending signals by radio from the nerve fibres to the computer, but also picking up signals from the computer, playing them down onto the nerve fibres.
But sending and receiving signals from the nervous system means that the new prototype will be much larger.
We are making connections onto the nerve fibres, 100 connections essentially, and those we have to feed through here and transmit those out. So instead of one signal, which was from the previous implant, we're looking at 100 signals off my nervous system.
Warwick's team hopes to record electrical nerve impulses like pain or movement and then replay those signals back into the arm to see how his body reacts.
But also, can we pick up extrasensory signals? Signals like on some of our little robots, ultrasonic signals, can we send them onto my nervous system to give me an extra sense? The robots with the white faces we call the Seven Dwarfs. They're actually using ultrasonics to sense the world around them, a bit like a bat senses the world. For our new experiment, I'll be having a sense just like them. In the future, maybe I can have light sensors and even infrared sensors as well. We can look to enhance the human in order to make us sense all different ways. This robot now is just using ultrasonic sensors, and it's been set up to stay some distance away from me as I move this way. Come on, come on, come on, come on. It follows me just using ultrasonic signals. There, don't be scared. Ah! With the new experiment, it's really trying to push back the frontiers and look ahead, but there are all sorts of medical spin-offs. Ultrasound going in as an extra sensory input. For me, maybe it's an extra, it's cool, but for somebody who's blind, it could be used to replace their blindness, to give them an ability to detect obstacles nearby. So there are potential immediate spin-offs, but in the long term, who knows where it's going to take us.
Wherever we see future research going, one thing is clear. Connecting directly to the human nervous system and ultimately the brain is the biggest goal in cyborg science.
We know very little about the brain. You must realize that the brain is the most complex machine on earth, and that takes a little bit of time to unravel. The people who are doing it are neurologists, and they're trying to discover how the 10 billion neurons that we have in our head actually work together with one another. So in order to perhaps try and work out what the brain is thinking by sensing it with some sort of microchip would be enormously difficult.
Considering we find it hard even understanding primitive fish brains, connecting high technology to the human nervous system seems impossible. But in Chicago, the creation of an amazing half-fish, half-robot is already paving the way. Taking a lamprey fish, the researchers remove the brainstem, keeping it alive in salt water. This disembodied brain is connected via computer to a small robot. Electronic eyes on the robot sense lights, sending signals to the brain. In return, the lamprey brain sends its natural impulse back to the robot, instructing it to move towards the light. The unique creature is passing signals both ways from fish brain to robot and back again.
In the cells that we are looking at in the lamprey, these are cells, as I said, of the reticular formation. There is a particular structure that is in humans as well. And we hope that by understanding how this mechanism can control a simple robotic device, we are a step closer to know how activities from cells in parts of the human nervous system can be trained to control artificial prosthesis.
Other researchers have looked at animal brains, connected them to computers, and seen within a feedback loop how we can change how the animal thinks and so on. What I would like to do is to push forward as far as humans are concerned and see how we can change the way the human operates, using the same sort of feedback loops.
Establishing two-way sensory feedback is theoretically leading the way to new treatments for conditions like blindness or paraplegia. Apart from many potential benefits, are there also ethical implications to cyborg research?
We can see millions of opportunities for these new technologies, but we don't know what people are going to accept. We don't know what people are going to try and abuse. And at some point, we will need a lot of regulation to regulate what people can do with these various things. We don't even know what all of their capabilities will be, but we have to protect the individuals against the big brother type abuse.
This is what's technically possible now. I believe we need very quickly international legislation and international bodies to oversee what's going on with implants. There are enormous questions as far as privacy of the individual and should you decide you can have an implant? If not, who else should decide? These are vital questions that need to be addressed not only now, but in the years ahead.
Debate over future research is starting, but many scientists already see us as cyborgs simply by interacting with technology like the internet, mobile phones, and even mechanized transport. Although technology is allowing us to do new tasks, will we remain the same people as before?
We must retain our biological drives, otherwise our entire raison d'etre on Earth will change. How much of our systems we can actually replace by artificial non-biological systems is an open question. I think you very rapidly would get to the point where you virtually lose an individual's consciousness if you put in too many chips.
Despite high-tech components, it's impossible to see people like Daisy or Chris as anything other than human beings. But could new developments make them even more advanced than the rest of us?
In the future, limbs could be such to the extent that you could get Paralympic athletes that actually have to compete on a different level simply because they're better than able-bodied athletes.
It's very difficult to say at what point does a prosthetic become more efficient than a real leg? Will that point ever be reached? I think the important thing to bear in mind in all of this is that it is about enabling people to achieve their personal best.
Evolution developed using tools to build extensions of our body for greater survival. Society has long idolized perfection in the human form, and there is growing desire for cosmetic surgery. Will we now want to improve on nature by upgrading the body to interact efficiently in more technological environments?
I think people are accepting the whole idea of robots much more than when we first started about 20 years ago. They're not so freaked out by it. I can imagine myself in 100 years' time being part human and part robot.
We're living in a very interesting time. Over the next 15 years, we're going to produce computers which are almost as smart as we are. That's going to force us to start thinking about what it really means to be human. We've never had to make those decisions before. We just get on with the business of survival.
Understanding technology is now a survival tool, and integrating humans with computer hardware is fast becoming reality.
If we give ourselves some of the capabilities that computers and other machines have, we can actually step forward and grab hold of more advantages ourselves. So it's a bit like a designer evolution. We can decide which way we go.
Should we be thinking less about what's possible in cyborg science and more about where these technologies will take us as a society and a species?